Okay, good evening, everybody. Mass settlement, how utopia could materialize. We just choose this title to show that we are interested in the process to go from utopia to reality. And we will focus on the feasibility and realism. Well, first you have this image of a district of the colony, and as you see, it looks fairly simple, but it should be, because we have to build it and we have to maintain it. So our rationale is built on the idea that reusability, as innovated by Elon Musk, induces lower costs and therefore feasibility, together, of course, with the previous innovation or ideas which has been essential, that is ISRU. And we are proposing a technical study, not an industrial blueprint, but an effort to rationalize and document the case. And, well, some weaknesses that we don't want to enter into some futuristic consideration. And we want to give substance to economic analysis. We have been studying this for a few years with Richard Edman. Okay, significant points raised. We dream of establishing a new branch of mankind, but for the time being, it's not yet the moment. We'll see later when, after this 1,000 colony becomes viable. But what is most important is to create a commercial venture which will be mass specific, and which, with as little as a few transfers from Earth as possible, mass transfers. And the idea is to commercialize residency services supply. This will be the main income of the colony, and it will be for anybody interested to come, provided they pay. That is scientists, tourists, and also freelance entrepreneurs, some people who want to create something. And in order to assess the need, that is the expenses and the income possible, we built an economic model so that we'll discuss later. And for us, the real challenges are not related to the equipment technologies, because they are building up, but rather in raising their RAMs, that is to unprecedented level, because we really need, first of all, reliability. And the risk, the challenges are not related to the risk, because we think that people wanting to go to Mars will accept to take risk. So this is not our problem. But one of the most challenging action will be to the rate of building the colony, because we have little equipment available and a few people. Safety and health. This is the settlement or the colony will have, in this respect, necessity to support operators' actions. That it's mainly planning, and reduce human error risk, maximize risk situation awareness, and for strict environmental control, facilitate human adaptation, and this with the help of artificial intelligence. Well, we can discuss that also later, but for instance, one of my main preoccupation would be the microbial risks and the control of the quality of the environment. The aim of the study, Taking into account the operational needs, you see, customer satisfaction, volume of production, production rate, and also the different kinds of data and constraint, mass and cost data, working environment, safety and health, maximum. And we will use maximum ISRU and 3D printing. So on the right, you have what we could do with ISRU. On the left of the table, you have extracting minerals or using the atmosphere, and on the right side you have the out, which is, for instance, ethylene, polyethylene, methane, methanol, fertilizer. And at the bottom, you see that we can, by mining hematite or iron oxide, get steel, and with silicium get glass sheets. And these two products are essential for the colony because we will use them to build the colony. So, summary of the main option. For us, it is a choice of a site. It would be essential to have access to water ice and also to nice sceneries, because we will rely partly on the tourist business. And science will be performed in vicinity or outpost, but this is not a real problem because we can perform the science with robots, which will be under direct command with no time lag, since we are on the same planet. The layout we have to be aware that not only people will live, but they will have to move, and when they move out of their premises, they will not don a spacesuit. They will use corridors. So we have to combine easy internal communication and depressurization safety. Radiation shielding, that's another very important point. It will be, for us, we will build on the ground, and we will use either regolith, but it means that we would have to move a lot of land, of mass, and the other solution would be to use movable ice panels. And in this design, we show that we could have that kind of ice panels about 1 foot thick, 1 foot thick. So, pressurized modules, as you see, they are hexagonal cylinders of glass panel and steel. So they are, and of course with thermal insulation. So we take advantage of the two abundant resources on Mars, which is silicium and iron. And we use that for the habitat, which is the white covered, because it's ice covered part. We also use it for the corridors, which are under the habitat, and for the greenhouses, which are in front of the habitat. And the ice which is atop the window of the habitat is movable and can be and can protect the during when it is not necessary to look outside, can protect people inside from radiation. As you know, ice is a very good protector against solar energetic particle. Domes, that's the bottom illustration on the right. You see it's the same principle, but this time we use triangle. We create a kind of geodesic, half geodesic sphere, and we use triangle, and they are borne by steel beams. And of course, domes are necessary for all kind of meeting and people getting together. We are thinking of a maximum diameter for domes of 30 meters. Most of them will be 30 meters diameter, because we have to, in order that there will be only half a sphere, we will have to maintain them on the ground, of course, and be for the structure to be to hold, it will have to be very thick. For instance, it's 2 meters thick for 20 meters and 3 meters thick for 30 meter diameter. So it will be a base of duricrete. Greenhouses. That's another main option. People will mostly eat vegetables, and we have to look at the maximum energetic, dietetic, and organoleptic qualities, and also as much variety as possible. People will eat spirulina, vegetables, cereal, and so on. Fish, certainly, shrimps, poultry, maybe, but the hens are flying, and that could be a problem. We will look for minimum inedible waste and minimum 8 of the vegetables, because we have limited volume resources. Okay, so you see the details of this greenhouse, and we will use heating from the nuclear reactor. Power, because our power source will be nuclear, not fusion but fission. We computed the need from 3.5 million megawatt electric at the beginning, and 17 megawatt electric at the end of the period, which when we reach 1,000 people. It's about 20 years after the first or second launch. So for nuclear fission, we choose the mega power project, hoping that land will be able to make it operational. So these are the main data. I said 20 years for the building of the base until we reach 1,000 people. Each one will have 30 square meter lodging, but taking into account other common volume, each one will have 50 square meter surface available, and the greenhouse could be sufficient with a surface of 100 square meter. Of course, we will use several layers in the same volume, so we'll have smaller volume, smaller greenhouses. Mass to land at the beginning, 500 ton. At each launch window, 3 and 10 ton. Okay. 5 minutes? Okay. Financial structure. We expect space entrepreneurs to invest into a Mars Foundation, and then the public will buy stock of a Mars colony operating company, which will be also Mars Foundation will also be shareholders. Space Agency also shareholders, and we'll have a space bank and space insurance company to facilitate the gathering of money, especially for residents. Financial needs and resources. Income will come from selling trips to Mars, selling residencies on Mars, services on Mars, renting equipment on Mars, holding and trading stock of Martian venture. We do not expect exportation of ponderous matters or objects to Earth. And paying guests will provide this income. As you see, we expect a total expense of $50 billion, some $50 billion. And dividends to the shareholders will come after 20 years. Economic model, as I said at the beginning, the question is there a pricing leading both to a large enough market and to a satisfactory operational margin? And so we assess the size of the resident categories. There will be 550 staff and 450 paying guests. Most influential costs are the trip cost. We compared this cost with a histogram of household incomes in the USA. And we see that we can reach a balance after, of course, some 20 years, if we can get a payment of 4 to 6 million from the people, from the 450 people who will be residing in the station, in the settlement. Social and cultural aspect. Well, it's very important. Selection will be very important. And culture, as you see, of course, science and technology will come first, then medicine, general culture, and sports. As far as structure are concerned, this is what it looks complicated, but it is not so much. That is, since Mars Colony operating company would have invested so much money, the management of the colony will be made by a colony directory, which will be made of 3 or 5 people. And the staff and the resident, the paying guest, will be part of the colony executive council together with the colony directory to make decisions. And but colony directory and the operational department, which are vital to the colony, as well as the scientist operation department, will have a veto right in case a decision made by the colony executive council is not viable. Aesthetic will look to optimize design, never forget man, build on experience. Optimize design, 1 minute, okay. Well, this is it. Anyway, this is the keywords, and that's it. So the 3 of us, Richard Mine, Tatiana Volkova, who unfortunately could not be here, and myself. Well.
All right, thank you. Questions for this presenter? Any questions in the front row here or anywhere else in the audience? There we go.
Well, since you didn't have time to elaborate on it, elaborate a bit on the aesthetics of your colony.
I didn't catch it.
Elaborate a bit on the physical aesthetics of what's this thing going to look like?
Of this?
The colony.
Oh, the colony, yes. So the colony will be made of several resident quarters of 200 people, and they will be centered on a hub which will be collective to the other, to all the quarters. We did not want to make a round, fancy construction because of the difficulty to build it and to maintain it. So we'll have access from the outside with equipment and with rovers up to the center. And, well, it goes fast. We'll have, this is in the corridor. In the corridors, we'll have a view outside. This is a production of glass, and this will be outside of the residence area, and as well as, of course, the nuclear reactor. Maybe if we find a cliff, we can build that kind of thing. It will be for longer residents. They could be better protected against radiation. But with a 2-meter regolith and 1 foot thick of ice, we could have a fairly good protection. This is again the ISRU scheme.
All right. With that being ado, let's give a big round of presentation.